Have you ever looked up at that reddish dot in the night sky and wondered how long it would actually take to get there? Mars, our cosmic neighbor, shining like a distant beacon in the darkness. Today, we will see why the answer isn't as simple as you might think, because the universe doesn't play by the rules we're used to down here on Earth. Are you ready? Let's get started. Right now, you're standing on a planet that's hurtling through space at about 107,000 kilometers per hour around the Sun. Mars is doing the same thing, except at a different speed, about 86,800 kilometers per hour, and on a different track. So when someone asks how long it takes to reach Mars, the first question we need to ask back is, when are you leaving? Because timing, as it turns out, is everything when you're trying to catch a ride to another planet. Let me paint you a picture of the challenge we're facing. Imagine you're standing on a spinning carousel, and you're trying to jump to another carousel that's also spinning, but at a different speed and on a different sized circle. You can't just leap whenever you feel like it. You have to wait for exactly the right moment when both carousels line up just right. That's essentially what we're doing when we send spacecraft to Mars, except our carousels are planets, and we're playing this game across millions upon millions of kilometers of empty space. The distance between Earth and Mars isn't constant. It changes dramatically depending on where both planets are in their orbits. At their closest approach, called opposition, Earth and Mars can be as near as 54.6 million kilometers apart. That might sound like a staggering distance, and it is, but here's where it gets wild. At their farthest, when they're on opposite sides of the Sun, that gap balloons to a mind-boggling 401 million kilometers. That's more than 7 times the closest distance. Think about that for a moment. We're talking about a target that moves, on a path we can't control, at a distance that varies by hundreds of millions of kilometers, and we're trying to hit it with a spacecraft launched from another moving platform, our own rotating, orbiting Earth, using technology that has to work perfectly for months on end in the hostile void of space. The mathematics of getting to Mars relies on something called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who figured out this elegant solution back in 1925. Almost a century ago, before humans had even broken the sound barrier, this visionary thinker was calculating trajectories to other worlds. His solution was beautiful in its efficiency. Instead of trying to fly straight at Mars like you might drive a car to a destination, you use gravity and orbital mechanics to your advantage. Here's how it works. When a spacecraft leaves Earth, it doesn't immediately head toward where Mars is at that moment. That would be like throwing a football to where the receiver is standing now. Instead, it aims for where Mars will be months from now, like a quarterback leading a receiver downfield. The spacecraft enters an elliptical orbit around the Sun that's perfectly calculated so that when it reaches the far end of that ellipse, Mars will be right there waiting for it. This cosmic rendezvous requires launching during what we call a launch window. These windows open roughly every 26 months when Earth and Mars align in what's known as favorable opposition. Miss your window, and you're waiting more than 2 years for the next opportunity. It's like catching a bus that only comes by twice a decade, except this bus costs billions of dollars and carries humanity's dreams of becoming a multiplanetary species. But here's what makes this journey even more challenging. It's not just about getting there. The laws of orbital mechanics that govern how we travel between planets create what scientists call the trajectory problem. You can't simply turn a spacecraft around in space like you'd make a U-turn in a car. There's no friction to slow you down, no road to push against. Everything depends on velocity, gravity, and the careful ballet of orbital mechanics. Let's look at some real missions to understand what this actually means in practice. NASA's Mariner 4, which became the first spacecraft to successfully fly by Mars back in July of 1965, took 228 days to make the journey. That's roughly 7.5 months of travel through the void. The images it sent back, grainy, black and white photos of a cratered, seemingly dead world, traveled back to Earth at the speed of light and still took minutes to arrive. Fast forward to more recent missions. The Mars Reconnaissance Orbiter, launched in August of 2005, took 7 months to reach Mars. The Curiosity rover, that incredible mobile laboratory that's been exploring the red planet since August of 2012, also spent about 7 months in transit. Perseverance, NASA's latest rover that landed in February of 2021, had a similar journey time, about 7 months from launch to landing. Notice a pattern? Despite decades of technological advancement, despite computers that are millions of times more powerful than those used during the Apollo era, despite revolutionary improvements in rocket technology, we're still taking roughly the same amount of time to get to Mars. Why? Because we're still using the same fundamental approach, the Hohmann transfer orbit. It's the most fuel-efficient way to get there, and when you're launching payloads that cost hundreds of millions or billions of dollars, efficiency matters enormously. But here's where things get really interesting, and where we start to see the limits of our current approach. That 6 to 9 month journey isn't just inconvenient, it's one of the biggest obstacles to human exploration of Mars. Think about what happens to the human body during that time in space. Astronauts on the International Space Station, orbiting just 400 kilometers above Earth's surface, experience bone density loss of about 1 to 2% per month. Their muscles atrophy, despite rigorous daily exercise routines. Their vision changes as fluids shift in the zero-gravity environment. Their immune systems become compromised. And crucially, they're still protected by Earth's magnetic field, which shields them from much of the dangerous cosmic radiation that permeates deep space. On a journey to Mars, astronauts would be leaving that protective bubble. They'd be exposed to galactic cosmic rays, high-energy particles from exploded stars, from supernova remnants scattered across the galaxy, carrying energies so intense they can pass right through spacecraft walls, right through human tissue, damaging DNA and increasing cancer risk with every passing day. They'd face solar particle events, sudden bursts of radiation from our sun that could deliver lethal doses if astronauts were caught outside during a major flare. 7 months of this exposure. 7 months of muscle and bone loss. 7 months of psychological stress from being confined in a small space with the same handful of people, with Earth becoming an increasingly distant speck, with no possibility of rescue if something goes catastrophically wrong. And then, after all that, you still have to land on Mars, establish a base, conduct your mission, and face the return journey. Another 7 months back home. This is why scientists and engineers have been asking a crucial question. Can we go faster? The answer is yes, in theory. But as with everything in space exploration, the gap between theory and practice is filled with enormous challenges. To go faster than a Hohmann transfer allows, you need more energy. A lot more energy. You need to accelerate harder when leaving Earth, maintain that velocity, and then slow down when you reach Mars. Every bit of extra speed requires exponentially more fuel, and fuel has mass, and mass requires more fuel to lift, which adds more mass, which requires even more fuel. It's a vicious cycle that rocket scientists call the tyranny of the rocket equation. Konstantin Tsiolkovsky, a Russian scientist who was dreaming of spaceflight back in the late 1800s and early 1900s, derived the mathematical relationship that still governs everything we do in rocketry today. His equation tells us something profound and frustrating. To go faster, you need to carry more propellant, but the propellant itself has mass that you need to accelerate, so you need even more propellant to move that propellant, and on and on. It's diminishing returns all the way up. This is why chemical rockets, the kind we've been using since the dawn of the space age, have fundamental limitations. They work by burning fuel and oxidizer, creating hot gases that blast out of a nozzle to produce thrust. They're powerful enough to lift massive payloads off Earth's surface against gravity's relentless pull. The Saturn V rocket that sent astronauts to the moon produced an astounding 34 million newtons of thrust. That's roughly equivalent to the power of 85 Hoover dams, all concentrated in a controlled explosion beneath the spacecraft. But once you're in space, where you don't need that enormous power to fight gravity, chemical rockets become inefficient. They have what's called low specific impulse, which is essentially a measure of how efficiently a rocket uses its propellant. It's like the gas mileage of a rocket engine. Chemical rockets have a specific impulse typically ranging from 200 to 450 seconds, depending on the type of propellant and engine design. To put that in perspective, imagine you have a kilogram of propellant. A chemical rocket with a specific impulse of 300 seconds can use that kilogram to produce thrust for 300 seconds. After that, the propellant is gone, expelled into space as exhaust. If you want to keep accelerating, you need to carry more propellant, which means more mass, which means you need even more propellant to move that mass, and you're right back in the tyranny of the rocket equation. So scientists started thinking, what if we could use a different kind of propulsion? Something that's much more efficient, that can run for months or even years on a relatively small amount of propellant. Something that trades raw power for endurance, sprint for marathon. Enter ion propulsion, one of the most elegant and revolutionary concepts in spaceflight. Instead of burning chemical fuel, ion drives use electricity to strip electrons from atoms, usually xenon or krypton gas, creating charged particles called ions. These ions are then accelerated by electric fields to incredibly high speeds and expelled from the spacecraft. The reaction force pushes the spacecraft in the opposite direction, just like any rocket, but with one key difference. The exhaust velocity is much, much higher. While chemical rockets expel exhaust at speeds of around 2 to 5 kilometers per second, ion drives can achieve exhaust velocities of 20 to 50 kilometers per second, or even higher. That might not sound like a huge difference, but remember, it's all about efficiency. Higher exhaust velocity means better specific impulse. Ion drives can achieve specific impulses of 3,000 to 10,000 seconds or more. That's 10 to 30 times more efficient than chemical rockets. NASA's Deep Space One mission, launched in 1998, demonstrated that ion propulsion could work in real space conditions. The spacecraft's ion engine operated for a total of 16,000 hours. That's over 660 days of continuous thrust. Imagine a car engine that could run non-stop for nearly 2 years without refueling. That's the kind of endurance we're talking about. But here's the catch with ion drives. They produce incredibly tiny amounts of thrust. The Deep Space One engine generated about 92 millinewtons of thrust. To give you a sense of scale, that's about the weight of a single sheet of paper pressing down on your hand. You could produce more thrust by gently blowing air out of your mouth. It's almost comically weak compared to the thunderous power of chemical rockets. Yet over time, this whisper of thrust adds up. Because ion drives can run continuously for months or years, they gradually accelerate the spacecraft to higher and higher speeds. It's like the difference between a sprinter and an ultra-marathoner. The sprinter explodes off the blocks with tremendous power but runs out of steam quickly. The marathoner starts slow but maintains that pace for hours, eventually covering far greater distances. NASA's Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres between 2007 and 2018, used ion propulsion to achieve something no chemical rocket could have done efficiently. It became the first spacecraft to orbit 2 different extraterrestrial bodies, using its ion drive to escape from Vesta's orbit and travel onward to Ceres. The mission changed its velocity by more than 11 kilometers per second over its lifetime, a feat that would have required enormous amounts of chemical propellant. So could we use ion drives to get to Mars faster? The answer is complicated. Ion propulsion excels at efficiency, not raw speed. While an ion-driven spacecraft could potentially achieve higher final velocities than a chemical rocket using the Hohmann transfer, it would take time to build up that speed. The spacecraft would need to spiral outward from Earth's orbit, gradually climbing away from the Sun's gravity well, then spiral inward to intercept Mars. Chemical propulsion using a Hohmann transfer, even though it uses less propellant. You're trading time for fuel efficiency. For cargo missions where speed isn't critical, that's an excellent trade-off. For human missions where every day in space increases radiation exposure and health risks, it's less appealing. But what if we could combine the efficiency of electric propulsion with much more power? What if instead of generating thrust equivalent to a piece of paper, we could generate thrust equivalent to hundreds or thousands of pieces of paper while still maintaining that incredible fuel efficiency? This is where things get exciting, because we're living in a time when the theoretical is becoming practical. Scientists and engineers are developing what's called high-power electric propulsion, ion drives, and similar technologies that are scaled up dramatically from the pioneers like Deep Space One and Dawn. NASA's evolutionary Xenon thruster, or NEXT, represents a significant leap forward. It's an ion engine that produces up to 236 millinewtons of thrust, more than twice what Deep Space One achieved, while maintaining a specific impulse above 4,000 seconds. It's been tested on the ground for over 48,000 hours, demonstrating reliability that would make it suitable for long-duration missions. Even more ambitious is the X-3 thruster, a type of Hall-effect thruster developed by researchers at the University of Michigan and tested at NASA's Glenn Research Center. In 2017, it broke records by achieving 5.4 newtons of thrust. That's about 58 times more than Deep Space One's engine, while operating at 100 kilowatts of power. That might still sound weak compared to chemical rockets, but remember, it can run continuously and it's incredibly efficient. The challenge with high-power electric propulsion isn't the thruster technology itself, it's generating enough electricity to power these engines in space. Solar panels work near Earth, where sunlight is abundant, but as you travel farther from the sun, solar power drops off dramatically. By the time you reach Mars's orbit, which is about 1.5 times farther from the Sun than Earth, solar panels receive less than half the energy they would near Earth. Venture out to Jupiter, and you're getting less than 4% of the solar energy available near Earth. This is where nuclear power enters the picture, and this is where the future of Mars travel gets truly revolutionary. For decades, nuclear power in space has been limited to radioisotope thermoelectric generators, RTGs, which use the heat from radioactive decay of plutonium-238 to generate electricity. These have powered everything from the Voyager probes, now sailing beyond the edge of our solar system, to the Curiosity and Perseverance rovers exploring Mars right now. RTGs are reliable and long-lasting. Voyager 1 and 2 have been operating on their nuclear power sources since 1977, nearly 5 decades ago, but they produce relatively modest amounts of power. Curiosity's RTG generates about 110 watts of electrical power, about enough to run a bright light bulb. That's sufficient for operating scientific instruments and keeping systems warm in the Martian cold, but nowhere near enough to power high-thrust electric propulsion. What we need for fast Mars transits is nuclear fission power, actual nuclear reactors operating in space, not using the passive heat from radioactive decay, but actively splitting uranium atoms in a controlled chain reaction to generate substantial amounts of electricity. This technology, called nuclear electric propulsion, or NEP, could provide the kilowatts or even megawatts of power needed to run high-thrust ion drives continuously throughout the journey to Mars. NASA, in collaboration with the Department of Energy, has been developing space nuclear reactor concepts for exactly this purpose. The Kilopower project, tested at the Nevada National Security Site, demonstrated a small nuclear reactor that could provide up to 10 kilowatts of electrical power, about 100 times more than an RTG of similar mass. Scaled-up versions could provide hundreds of kilowatts or more, enough to power electric propulsion systems that could significantly reduce Mars transit times. Imagine a spacecraft powered by a nuclear reactor generating 500 kilowatts of electricity feeding a cluster of high-efficiency ion or Hall-effect thrusters. This spacecraft could produce continuous thrust for the entire journey, gradually building up tremendous velocity. Instead of the 7 to 9 months required by a Hohmann transfer, a nuclear electric propulsion system could potentially cut that time to 4 or 5 months, maybe even less with more powerful systems. That might not sound like a massive improvement, shaving a few months off the journey, But for human crews, every week matters. Fewer weeks in microgravity means less bone and muscle loss. Fewer weeks of radiation exposure means lower cancer risk and less potential for damage to the central nervous system. Fewer weeks confined in a cramped spacecraft means better psychological health and crew cohesion. These reductions translate directly into healthier astronauts who are better prepared for the challenges of working on Mars. But nuclear electric propulsion, as promising as it is, still faces the fundamental limitation of electric propulsion: relatively low thrust. Even scaled-up versions would take days or weeks to build up significant speed. The spacecraft would still need to spiral away from Earth and spiral into Mars, which is time-consuming even if the total journey is shorter than a Hohmann transfer. So engineers started asking an even bolder question: what if we use nuclear power differently? What if instead of generating electricity to power ion drives, we use the nuclear reactor's heat directly for propulsion? This concept is called nuclear thermal propulsion, or NTP, and it's been around since the 1950s. The idea is elegantly simple. Instead of burning chemical fuel to create hot gas, you use a nuclear reactor to heat hydrogen propellant to extremely high temperatures, then expel it through a nozzle to create thrust. The reactor doesn't undergo a runaway reaction or explode. It's carefully controlled, just like a nuclear power plant on Earth. But instead of using the heat to boil water and spin turbines, you're using it to superheat your propellant. Because nuclear fission can achieve much higher temperatures than chemical combustion, nuclear thermal rockets can reach specific impulses of 800 to 1,000 seconds, roughly twice that of the best chemical rockets. That's not as efficient as ion drives, but here's the crucial difference. Nuclear thermal rockets produce much higher thrust. We're talking newtons measured in thousands or tens of thousands, not millinewtons. They have the muscle to actually push against gravity and accelerate quickly. This combination of decent efficiency and high thrust makes nuclear thermal propulsion incredibly attractive for Mars missions. A spacecraft using NTP could complete the journey in potentially 3 to 4 months instead of 7 to 9. That's cutting the transit time roughly in half, which means cutting radiation exposure in half, cutting the time spent in microgravity in half, cutting the psychological stress of confinement in half. The United States actually built and tested nuclear thermal rocket engines during the 1960s and early 70s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. Between 1959 and 1972, researchers built and tested more than 20 different reactor designs and engine configurations. These weren't just paper studies or computer simulations. They were actual nuclear rockets, fired up in the Nevada desert, producing tens of thousands of newtons of thrust while achieving specific impulses above 800 seconds. The NERVA program demonstrated that nuclear thermal propulsion was technically feasible. The engines worked, they were controllable, they could be restarted multiple times. They could run for extended periods. One engine logged over 110 minutes of operation at full power, which doesn't sound like much until you realize that's enough burn time to get you from Earth orbit to Mars trajectory and back. So why aren't we using nuclear thermal rockets today? The answer, as with so many things in space exploration, comes down to politics, priorities, and funding. The NERVA program was designed to support missions beyond the Apollo moon landings, missions to Mars, missions to the outer planets, establishing permanent bases in space. But by the early 1970s, the political will and public enthusiasm for ambitious space exploration had waned. The Apollo program was winding down. The Vietnam War was consuming resources and attention. NASA's budget was being cut dramatically. In 1972, the NERVA program was canceled. Not because it failed technically, it succeeded remarkably well, but because there were no missions on the horizon that required it. Why develop expensive nuclear rocket engines if you're not planning to send humans beyond Earth orbit? For decades, nuclear thermal propulsion remained a fascinating historical footnote, occasionally revived in concept studies, but never funded for actual development. Meanwhile, we continued sending missions to Mars using the same chemical propulsion and Hohmann transfer orbits we've been using since the 1960s. But something remarkable has happened in recent years. The dream of sending humans to Mars has reignited. NASA has made Mars exploration a long-term goal. Private companies like SpaceX are developing the heavy lift capabilities needed for Mars missions. The conversation has shifted from if to when and how. And with that shift has come renewed interest in nuclear propulsion. In 2023, NASA and the Defense Advanced Research Projects Agency, DARPA, announced a collaboration to demonstrate nuclear thermal propulsion in space. The program, called DRACO, Demonstration Rocket for Agile Cislunar Operations, aims to launch a working nuclear thermal rocket engine into space as early as 2027. Think about that timeline. Within just a few years, we could see the first nuclear thermal rocket operate in the environment it was designed for, the vacuum of space. This wouldn't be a paper study or a ground test in a bunker. It would be an actual demonstration that nuclear thermal propulsion can work as a practical technology for deep space missions. The DRACO program represents more than just a technology demonstration. It signals a fundamental shift in how we think about deep space exploration. For over half a century, we've been constrained by the limitations of chemical rockets. We've accepted that Mars is 7 to 9 months away because that's what the physics of chemical propulsion and orbital mechanics dictates. But with nuclear thermal propulsion, we're no longer bound by those same constraints. A nuclear thermal rocket could potentially cut the Mars journey down to 3 or 4 months. Some advanced designs using higher performance reactor configurations and optimized propellant flow might push that even lower, perhaps as little as 2 to 3 months for the fastest trajectories. Suddenly, Mars doesn't feel quite so impossibly distant. We're talking about journey times comparable to historical sea voyages, like sailing from Europe to the Americas in the age of exploration. But engineers and physicists are thinking even bigger. What if nuclear thermal propulsion is just the beginning? What if we could combine the high thrust of nuclear thermal systems with the efficiency of electric propulsion? This hybrid concept is called nuclear thermal electric propulsion, and it's exactly what it sounds like. You use a nuclear reactor that's powerful enough to both heat hydrogen for thermal thrust and generate electricity for ion or Hall effect thrusters. During high-thrust maneuvers, like breaking away from Earth orbit or entering Mars orbit, you run in thermal mode, getting maximum power. During the cruise phase between planets, you switch to electric mode, using high-efficiency ion drives to continue accelerating while conserving propellant. It's the best of both worlds. Raw power when you need it, endurance and efficiency when you don't. Theoretical studies suggest that nuclear thermal electric systems could reduce Mars transit times to as little as 60 to 90 days. 2 to 3 months. That's approaching the threshold where the health risks of space travel start to become manageable with current medical technology and countermeasures. Now, I know what some of you might be thinking. Nuclear rockets in space. Isn't that dangerous? What if something goes wrong during launch? What if the reactor malfunctions? These are legitimate concerns, and they deserve honest answers. First, it's important to understand that a nuclear thermal rocket isn't a bomb. It can't explode like a nuclear weapon, no matter what happens. Nuclear bombs require incredibly precise conditions, compressing fissile material to critical mass with split-second timing. A reactor is designed to sustain a controlled chain reaction, not create a runaway explosion. The worst-case scenario in a reactor accident is a meltdown where the reactor overheats and potentially breaks apart, releasing radioactive material, but not an explosive detonation. Second, modern nuclear thermal rocket designs incorporate multiple safety features. The reactor would not be activated until the spacecraft is safely in orbit or on its way out of Earth's vicinity. If a launch failure occurred, the reactor would fall back to Earth intact and inactive, just a very expensive piece of radioactive metal, but not critically different from the radioactive materials we already have in various applications on Earth and in space. Third, we've already been flying nuclear materials into space for decades. Those RTGs I mentioned earlier, the ones powering Voyager, Curiosity, Perseverance, and dozens of other missions, contain plutonium-238, which is highly radioactive. The Cassini mission to Saturn, launched in 1997, carried 32.7 kilograms of plutonium-238. Despite concerns and protests from some groups, it launched safely, flew past Earth twice for gravity assists, and went on to revolutionize our understanding of Saturn and its moons over 13 years of operation. The nuclear fuel in a thermal rocket, typically highly enriched uranium, would actually be less radioactive at launch than the plutonium in an RTG, because the fission chain reaction wouldn't have started yet. It's after operation, when the fuel has been irradiated and fission products have built up, that it becomes intensely radioactive. This is why the reactor wouldn't be activated until well away from Earth. That said, any nuclear technology in space requires careful engineering, rigorous testing, and transparent communication with the public. The benefits need to be weighed honestly against the risks. For Mars missions, the calculus is compelling. Cutting transit time in half doesn't just make the mission easier, it could make the difference between astronauts returning healthy enough to walk off the spacecraft or returning with permanent health damage from radiation and microgravity exposure. But let's push even further into the realm of advanced propulsion. Because while nuclear thermal and nuclear electric systems represent near-term possibilities, technologies we could develop and deploy within the next decade or two, there are even more exotic concepts that could, in theory, reduce Mars transit times to mere weeks or days. One of these concepts is fusion propulsion. Instead of splitting heavy atoms like uranium through fission, fusion propulsion would fuse light atoms like hydrogen isotopes, the same process that powers the Sun and other stars. Fusion releases even more energy per unit of fuel than fission, and it produces far less radioactive waste. The exhaust velocity from a fusion rocket could reach thousands of kilometers per second, giving specific impulses measured in tens of thousands of seconds or more. With fusion propulsion, a spacecraft could potentially reach Mars in 30 to 45 days, depending on the specific fusion technology and trajectory. That's a journey measured in weeks, not months. Astronauts could leave Earth orbit, coast to Mars, and arrive before they've even fully adjusted to microgravity. The challenge with fusion propulsion is that we haven't yet achieved sustained, controlled fusion reactions here on Earth in a way that produces more energy than it consumes. Scientists and engineers have been working on fusion power for over 70 years, famously joking that practical fusion power is always 30 years away. Major experimental facilities like the National Ignition Facility in California and ITER in France are making progress. In December of 2022, NEF achieved a fusion reaction that produced more energy than the lasers put into the target, a historic milestone. But achieving fusion ignition in a laboratory is very different from building a compact, reliable fusion reactor that can operate continuously in space. The temperatures involved are measured in millions of degrees. The magnetic fields needed to contain fusion plasma are extraordinarily powerful. The engineering challenges are immense. Still, several research groups are exploring fusion propulsion concepts that might be more practical than traditional fusion power plants. One approach uses pulses of fusion reactions rather than trying to sustain a continuous burn, like detonating tiny fusion capsules in rapid succession behind the spacecraft, each pulse providing a small kick of thrust. Another approach, called the direct fusion drive, developed by Princeton Plasma Physics Laboratory, uses a type of reactor called a field-reversed configuration that might be more compact and manageable than traditional fusion designs. Are these technologies ready for Mars missions today? No. Will they be ready in 5 years or 10? Probably not. But 20 years from now? 30? It's not impossible. The history of spaceflight is filled with technologies that seemed impossibly distant until suddenly they weren't. In 1903, the Wright brothers achieved powered flight for the first time. 12 seconds of wobbly flight covering 37 meters. 66 years later, in 1969, humans walked on the moon. Progress, when it happens, can be astonishingly rapid. Beyond fusion, there are even more speculative concepts. Antimatter propulsion, where matter and antimatter annihilate each other in a burst of pure energy, could theoretically achieve exhaust velocities approaching the speed of light. A spacecraft powered by antimatter could reach Mars in days or even hours, depending on how much acceleration the human crew could tolerate. The problem with antimatter propulsion isn't just that we don't know how to build the engine, it's that we can barely produce antimatter at all. Creating a single gram of antimatter would require more energy than the entire world produces in a year using current technology. Scientists at facilities like CERN can create tiny amounts, we're talking individual atoms, which survive for fractions of a second before annihilating. We're nowhere close to the industrial-scale antimatter production and storage that would be needed for propulsion. Then there's the concept of beamed propulsion, where the spacecraft doesn't carry its own fuel at all. Instead, powerful lasers or microwave beams based on Earth or in Earth orbit shine enormous amounts of energy at the spacecraft, either heating an onboard propellant or pushing against a solar sail. The Breakthrough Starshot initiative is exploring this concept for sending tiny probes to the nearest star system, Alpha Centauri, at 20% the speed of light. Scaled appropriately, similar technology could accelerate larger spacecraft to Mars at tremendous velocities. These exotic propulsion systems, fusion, antimatter, beamed energy, exist in the space between science fiction and science fact. The physics allows them. The laws of nature don't forbid them, but the engineering challenges are so formidable that we can't predict when, or even if, they'll become practical. So let's return to what's achievable in the near term, because this is where the story gets practical and exciting in ways that directly affect the timeline for human Mars exploration. Right now, in 2026, several organizations are actively developing the technologies needed for faster Mars transits. NASA's Draco program is moving forward with nuclear thermal propulsion demonstrations. SpaceX is testing Starship, a fully reusable, super-heavy lift vehicle designed to carry 100 people to Mars using chemical propulsion and in-orbit refueling. Not faster than traditional transits, but making them routine and affordable. The strategy SpaceX is pursuing is interesting because it doesn't rely on exotic propulsion. Instead, it accepts the 7 to 9 month journey time, but makes up for it with sheer scale and reusability. If you can launch frequently, if you can refuel in orbit, if you can send multiple ships on every launch window, then maybe speed becomes less critical. It's like the difference between having one very fast train that runs once a month versus having many slower trains that run every day. Sometimes frequency and capacity matter more than speed. But NASA and other space agencies are taking a different approach, betting that propulsion technology will advance enough to make faster transits practical. The Artemis program, which aims to return humans to the moon and establish a sustained presence there, is partly about developing and testing technologies for eventual Mars missions. Nuclear power systems, advanced life support, in situ resource utilization, all of these technologies being developed for lunar exploration directly support Mars missions. There's also growing interest in using the moon as a staging point for Mars missions. Because the moon has much lower gravity than Earth, about 1/6, and no atmosphere, launching from the lunar surface requires far less energy than launching from Earth. A spacecraft assembled on the moon or in lunar orbit could carry more propellant, more cargo, more crew, without the tyranny of the rocket equation that makes Earth launches so challenging. Imagine this scenario. Components for a Mars spacecraft are launched from Earth to the moon on heavy-lift rockets. On the lunar surface or in lunar orbit, crews assemble the spacecraft, fuel it with propellant manufactured from lunar resources. There's water ice in permanently shadowed craters at the moon's poles that could be split into hydrogen and oxygen for rocket fuel, and then depart for Mars. The Earth-to-Moon leg of the journey takes only 3 days. The spacecraft never has to fight its way out of Earth's deep gravity well with all its Mars-bound cargo already attached. This approach doesn't necessarily make the Earth to Mars journey faster, but it makes the entire mission architecture more efficient and sustainable. And efficiency matters when you're trying to establish a permanent human presence on another world, not just plant a flag and leave. Another factor that influences Mars journey time is the trajectory itself. I've been talking primarily about Hohmann transfers and faster alternatives, but there's actually a spectrum of possible trajectories with different speed, energy, and timing trade-offs. A Hohmann transfer is the minimum energy trajectory, the most fuel-efficient path, but you could choose to use more energy, accelerate harder, and take a faster route. These are called high-energy trajectories or fast transits. With chemical rockets, you could theoretically cut the journey to Mars down to about 4 to 5 months using a high-energy trajectory, but you'd burn significantly more propellant, maybe twice as much or more. For robotic missions where every kilogram of payload is precious, that's usually an unacceptable trade-off. For human missions where crew health is paramount, it might be worth it. There are also gravity assist trajectories, where you swing by another planet, typically Venus, using its gravity to change your speed and direction. The Mariner 10 mission used Venus gravity assists to reach Mercury in the 1970s. For Mars missions, a Venus gravity assist could theoretically reduce the total delta V required, the change in velocity needed, but it often increases the total trip time and adds complexity. You're taking a longer route to save fuel, which is generally the opposite of what you want for human missions. Then there's the concept of cycling orbits, pioneered by astronaut Buzz Aldrin. An Aldrin cycler is a spacecraft that follows a trajectory that brings it close to Earth and Mars periodically, typically every 26 months, without using any propellant to maintain that orbit. It just loops endlessly between the two planets. Smaller ferries would carry crews and cargo from Earth up to the cycler as it swings by, then again from the cycler down to Mars at the other end, and vice versa for the return trip. The beauty of the cycler concept is that the main spacecraft can be massive and well shielded because it never has to land or take off from a planet. It just needs a small amount of propulsion for periodic course corrections. You could build a cycler with thick radiation shielding, spacious living quarters, artificial gravity generated by rotation, all the things that make a long-duration spaceflight more tolerable. The journey time wouldn't necessarily be shorter, but the journey itself would be far more comfortable and safer. What's fascinating is that all these approaches — chemical, nuclear thermal, nuclear electric, ion drives, cyclers, lunar staging — aren't mutually exclusive. The future of Mars exploration will likely involve a combination of technologies, each used where it makes the most sense. Chemical rockets might continue to be used for launching from planetary surfaces. Nuclear thermal propulsion might handle the main Earth-to-Mars transit. Ion drives might be perfect for cargo missions where time isn't critical. Cyclers might eventually carry regular passenger traffic once we've established bases on both worlds. We're living in a unique moment in history where these technologies are transitioning from theoretical concepts to practical engineering projects. The nuclear thermal rocket that will fly on the Draco mission is being built right now. The high-power electric thrusters that could enable faster Mars transits are being tested in vacuum chambers. The heavy lift rockets needed to launch these systems are on the launch pads. But let's be honest about the timeline, because that's important too. The Draco demonstration is scheduled for 2027, and that's assuming everything goes according to plan, which in aerospace often doesn't happen. Even if that demonstration succeeds brilliantly, proving that nuclear thermal propulsion works in space, it would still take years to develop an operational system rated for human spaceflight. You're looking at rigorous testing, safety reviews, building redundant systems, training crews. Realistically, the first human mission to Mars using nuclear thermal propulsion probably won't happen before the mid to late 2030s, maybe even the 2040s. Does that seem frustratingly distant? Maybe. But consider this. There are young people watching this video right now who could be on that first nuclear-powered mission to Mars. If you're 15 or 20 years old today, You could be 35 or 40 when that mission launches, prime age for an astronaut. The person who will first set foot on Mars using fast nuclear propulsion might be in high school right now, studying physics and dreaming of the stars. And here's something else to think about. The first missions won't have the fastest transit times. They'll be conservative, using proven technology, taking the safest routes even if they're slower. But each mission will push the boundaries a little further. The 5th or 10th mission to Mars might be significantly faster than the first. By the time Mars colonies are established and interplanetary travel becomes routine, maybe by the end of this century, the journey might be so quick and comfortable that people will look back at our 7-month chemical rocket transits the way we look back at months-long sea voyages in wooden sailing ships. Let's zoom out for a moment and consider what all of this means in the grand context of human history and cosmic exploration. Our species evolved in Africa roughly 300,000 years ago. For the vast majority of that time, the fastest anyone could travel was at a running pace, maybe 20 or 30 kilometers per hour for short bursts. The invention of horses and boats expanded our range, but for thousands of years, traversing a continent took months or years. Then, in an evolutionary eye blink, everything changed. The steam engine arrived in the late 1700s, railways in the 1800s, automobiles in the early 1900s, airplanes just decades later. By 1969, less than 70 years after the Wright brothers' first flight, we were landing on the moon. The exponential acceleration of transportation technology is one of the defining characteristics of modern civilization. But after the Apollo program, something strange happened. Our expansion into space slowed. We retreated to low Earth orbit. For over 50 years now, no human has ventured beyond a few hundred kilometers above Earth's surface. The International Space Station, humanity's furthest outpost, orbits at just 400 kilometers altitude, closer to Earth's surface than the distance between many major cities. It's as if, after Columbus reached the Americas, Europeans had said, "Well, that's interesting," and then spent the next 5 centuries just sailing around the Caribbean without ever venturing inland or exploring further. It seems almost absurd in retrospect, but that's essentially what we've done with space exploration. The renewed focus on Mars, the development of new propulsion systems, the involvement of private companies alongside government agencies, all of this represents a potential end to that half-century pause. We might be on the cusp of the next great expansion, the moment when humanity truly becomes a multiplanetary species. And the speed at which we can travel to Mars matters enormously for that expansion. If every journey takes 9 months, Mars will remain a destination for only the most dedicated explorers and scientists. If we can cut that to 3 or 4 months with nuclear propulsion, it becomes more accessible. Difficult and dangerous, certainly, but within the range of what adventurous people might accept. If future technologies can reduce it to weeks, Mars could become almost routine, a frontier world connected to Earth in ways we can only imagine today. Think about what a 3-week journey to Mars would mean. That's shorter than many ocean voyages in the age of sail. It's comparable to a long vacation. People could conceivably travel to Mars, spend time there, and return home within a single year. Scientists could conduct research on Mars with far less impact on their health. Engineers could troubleshoot problems in person rather than through delayed communications. Families could potentially visit loved ones working on Mars without it being a one-way, life-altering decision. But we're not there yet, and it's important to be realistic about the challenges that remain. Even with the most optimistic assessments of nuclear thermal propulsion, fusion drives, or other advanced systems, there are fundamental constraints we can't engineer around. One of those constraints is human physiology. We evolved in Earth's gravity, breathing Earth's atmosphere, protected by Earth's magnetic field. Our bodies are exquisitely tuned to this specific environment. Take us out of it, and things start to go wrong. The human cardiovascular system, for instance, has to work against gravity to pump blood from your feet to your brain when you're standing. remove gravity, and suddenly that system is overpowered. Blood pools in the upper body and head, causing facial puffiness, and those puffy-faced appearance astronauts get in space. Your body senses this fluid shift and thinks you have too much blood, so it starts eliminating fluid, reducing your overall blood volume. Your heart, no longer working as hard, begins to atrophy like any unused muscle. Your bones, no longer bearing weight, start to demineralize at an alarming rate. Even if we cut the Mars journey to 2 months instead of 7, astronauts would still experience these effects. Faster travel helps, but it doesn't eliminate the problem. This is why some spacecraft designs incorporate artificial gravity, spinning the spacecraft or sections of it to create centrifugal force that mimics gravity's effects. The problem is that creating comfortable artificial gravity requires either very large structures, a rotating ring hundreds of meters in diameter, or rapid rotation rates that can cause disorientation and nausea. It's a challenging engineering problem, and we haven't yet built a crewed spacecraft with artificial gravity, though concepts exist and could be tested. Another constraint is reliability. The faster you want to go, the more energetic your propulsion system, the more complex your spacecraft becomes. A nuclear thermal rocket is vastly more complicated than a chemical rocket. A fusion drive would be more complex still. Each additional system is a potential point of failure, and in deep space there's no roadside assistance. If something breaks catastrophically, the crew might have no option but to continue forward, abort back to Earth, or in the worst case, face disaster. This is why early Mars missions, even using advanced propulsion, will likely carry redundant systems and conservative safety margins. They'll have backup propulsion, backup power, backup life support. All of that adds mass, which requires more propulsion, which adds more mass. Once again, the tyranny of the rocket equation rears its head. The fastest theoretical transit time and the realistic transit time for a safe, reliable mission might be very different numbers. There's also the question of what happens at the other end. Getting to Mars quickly is one thing. Landing safely is another. When you arrive at Mars, you're traveling at tremendous velocity relative to the planet, potentially dozens of kilometers per second. You need to slow down enough to enter orbit or land, and that requires either aerodynamic braking using Mars's thin atmosphere, or propulsive braking using your engines, or some combination of both. Aerodynamic braking is mass efficient. You're using the atmosphere as a brake rather than carrying propellant, but it's tricky and terrifying. You're slamming into an atmosphere at hypersonic speeds, converting kinetic energy into heat. The spacecraft experiences brutal deceleration forces and extreme temperatures. The margins for error are razor thin. If your approach angle is too steep, you'll burn up or crash. Too shallow, and you'll skip off the atmosphere back into space. Every Mars landing mission so far has used some variation of entry, descent, and landing procedures that NASA engineers call 7 minutes of terror, the time between hitting the upper atmosphere and touching down on the surface, during which the spacecraft is entirely autonomous because radio signals take between 4 and 24 minutes to travel between Earth and Mars, making real-time control impossible. It's terrifying even with our current approach velocities. With faster transit missions arriving at higher velocities, it could be even more challenging. Propulsive braking using rocket engines to slow down is more controllable but requires carrying a lot of propellant all the way to Mars, which makes the spacecraft heavier, which requires more propellant to get there in the first place. SpaceX's approach with Starship involves both aerodynamic braking to shed most of the velocity, then propulsive landing for the final descent. But Starship is designed for chemical propulsion trajectories. A spacecraft arriving from a nuclear thermal fast transit might need different techniques. With current chemical propulsion and Hohmann transfers, the answer is 7 to 9 months. With near-term nuclear thermal propulsion that could be demonstrated within the next decade, we're looking at 3 to 4 months. With more advanced nuclear, electric, or fusion systems that might arrive in the decades beyond that, potentially 30 to 60 days. with far future technologies like antimatter or beamed propulsion, theoretically days or even hours, though those remain firmly in the realm of speculation. But here's what's important to understand. We're not waiting for perfect technology before we go to Mars. The history of exploration shows that humans have always pushed forward with whatever technology was available, accepting risks and challenges that seem almost insane in retrospect. Magellan's crew circumnavigated the globe in wooden ships that would sink if you looked at them wrong, taking 3 years and losing 234 of the original 270 crew members. Yet they succeeded, and they changed the world. The first human missions to Mars will likely use technology that's good enough, not perfect. They'll take 7 or 8 months, not 3. The astronauts will face radiation exposure, bone loss, muscle atrophy, psychological stress, and 1,000 other challenges. Some people think we should wait, that we should perfect the technology first, make it safe and comfortable before we attempt such a dangerous journey. But I would argue that's backwards. We don't develop revolutionary technology by waiting, we develop it by doing. The Hohmann transfer orbits we've been discussing were first described in 1925 by Walter Hohmann, decades before we had the rockets to actually use them. Ion propulsion was theorized in the early 1900s, but wasn't demonstrated in space until Deep Space One in 1998. Nuclear thermal propulsion was proven in the 1960s and then shelved for 50 years because there were no missions to use it for. It's the missions that drive the technology, not the other way around. When President Kennedy committed America to landing on the moon by the end of the 1960s, we didn't have the rockets to do it. We didn't have the spacecraft, the spacesuits, the navigation systems, or the computers. We barely had the knowledge of what would be required. But that commitment, that deadline, that mission created the urgency and focus needed to develop all of those technologies in less than a decade. The same will be true for Mars when we commit to a date, whether it's 2035 or 2040 or 2045, when we say, we're going and we're going then, that's when the technology will mature. Nuclear thermal propulsion will get the funding and attention it needs. Advanced life support systems will be perfected. Radiation shielding will improve. In situ resource utilization will be demonstrated and refined. And then, once we've made those first difficult journeys with the primitive technology of the 2030s or 2040s, which will seem primitive to future generations even if it seems advanced to us now, that's when the real improvements will begin. The first spacecraft to Mars using nuclear thermal propulsion might take 3.5 months. The 10th might take 2.5. By the 100th, we might have fusion drives cutting the journey to 6 weeks. By the time there are permanent settlements on Mars, by the time children are being born there and growing up with dual citizenship on 2 worlds, the journey might be so routine and quick that nobody thinks twice about it. I want to leave you with one final thought about perspective and time. Right now, in 2026, Mars is an impossible distance away. It's a place we've only touched with robots, a destination that exists primarily in our imagination and scientific data. The idea of humans living and working there seems like science fiction to most people, but look back 50 years to 1976. That was the year the Viking landers touched down on Mars, the first spacecraft to successfully operate on the surface. At that time, the idea of rovers the size of cars exploring Mars, flying helicopters in its thin atmosphere, and preparing for human missions would have seemed like fantasy. Yet here we are, having done all of that. Look back 100 years to 1926. Aviation was still in its infancy. The idea of flying to another planet would have seemed literally insane, the stuff of Jules Verne novels, not serious discussion. Yet within 43 years of 1926, we landed on the moon. Now look forward 50 years to 2076. What will be possible then? If our progress continues, if we maintain focus and investment in space exploration, If the technologies we're developing today mature as expected, humans in 2076 might look back at our 7-month chemical rocket transits to Mars the way we look back at wooden sailing ships crossing the Atlantic. They might take a high-speed transport to Mars, arriving in 3 weeks, wondering how anyone ever had the courage to spend months in space with primitive early 21st century technology. Or maybe the progress will be even faster. Maybe fusion propulsion will be cracked in the 2040s, and by 2076, the Earth-Mars journey will take days. Maybe some completely unexpected breakthrough, a discovery in physics we haven't even imagined yet, will make interplanetary travel as easy as intercontinental air travel is today. The history of technology is full of surprises, innovations that came from unexpected directions and changed everything. What we do know is this: the journey to Mars is getting shorter. The technology is advancing. The commitment is building. The question isn't really, how long does it take to reach Mars? The question is, how long will it take before reaching Mars is so quick and routine that nobody asks that question anymore? And the answer to that question depends, in part, on all of us. On the students studying aerospace engineering and physics who will design the next generation of propulsion systems. On the policymakers who allocate funding for space exploration. On the public that supports or opposes these efforts. On the engineers and technicians building the hardware. On the astronauts who will take those first dangerous journeys, knowing the risks but going anyway because some destinations are worth reaching regardless of the cost. The road to Mars is long for now, but it's getting shorter with every year, with every advance in propulsion technology, with every successful test and demonstration. We're living in the transition period, the era when Mars shifts from impossible to difficult to merely challenging. Future generations will look back at this time as the beginning, the moment when humanity took its first real steps toward becoming a spacefaring civilization spanning multiple worlds. So how long does it really take to reach Mars? Today, 7 to 9 months with chemical rockets. Tomorrow, maybe 3 to 4 months with nuclear thermal propulsion. The day after that, perhaps weeks, with fusion drives or other advanced technologies. And someday, maybe sooner than we think, the answer might be long enough to watch a few movies and have a good meal, a footnote in a travel itinerary rather than an epic journey. That's the future we're building toward, one mission at a time, one technological breakthrough at a time. And if you're watching this, you're living through the very beginning of that transformation. That's something special. That's something worth paying attention to. Check out the video on the screen to discover why a Mars colony would collapse within months. If you're searching for the truth about Mars colonization, dangers of building a Mars base, or want to know why human missions to Mars could fail so quickly, this video is for you.